Johannes.
Hi, Anastasia. Hi, everyone.
Our next speaker is Johannes Henn from Munich, and he is going to tell us about first non-planar corrections to the Cusp anomalous dimensions in N equals 4, super Yang-Mills, and QCD. Johannes, please share your screen with us.
Thank you so much, Anastasia. Indeed, this is my first Zoom talk. So while I'm figuring out how to share the screen, let me thank you and the organizers for setting this up. This is really fantastic. Can you remind me where I need to share the screen?
Yes, if you could please click a button called share screen, we would be able to see your slide.
Indeed, indeed. Thank you.
Fantastic.
All right. So
Perfect.
let me just go to full screen mode and then we're ready to go.
Perfect.
Yeah, again, thank you and all the other organizers. I think it's really fantastic that we can have this online conference despite the current situation. So I'd like to talk about joint work with Bernhard Mistelberger and Grisha Kochemsky. And it's about the Cusp anomalous dimension. Now, let me start with an outline. I'm going to begin by giving some general motivation why we're interested in this particular anomalous dimension. And then I'm going to focus on the first non-planar corrections for this quantity. We're going to compute those, and we're going to also be interested in how it changes between N equals 4 and QCD. We're going to see that it's actually very, very much related. The computation uses an interesting method, kind of an unusual method that is based on a Wilson loop with a Lagrangian insertion. So I'll also tell you about that. And after that, I'll discuss the results and conclude. So to begin with, some motivation. Well, the Cusp anomalous dimension, by definition, comes from Wilson loops. If you have a Wilson loop of this shape with a cusp, then it describes the short distance singularities. And we're going to be interested in the case where these segments are light-like when you get a double pole, and the coefficient at one loop is the Cusp anomalous dimension. Beyond appearing in Wilson loops, it's really a universal quantity that governs many physical processes. For example, it appears as the high spin limit of the anomalous dimension of composite operators. Also, very prominently, it governs the infrared singularities of scattering amplitudes, and it also appears in the high energy limit. So these are just a few cases. More generally, I would say that in more or less any singular limit that you wish to take, it's in a gauge theory, it's quite likely that this object shows up. Now, oops, overshot here. Now, famously, the planar Cusp anomalous dimension in N equals 4 super Yang-Mills is one of the first cases of an exactly known quantity. And this is shown in this plot where on the vertical axis, you have gamma cusp divided by G. So this normalization is chosen such that it still vanishes at low coupling and goes to 1 at strong coupling. And the horizontal axis goes from weak to strong coupling, except that I rescaled the positive axis just to the interval 0 to 1. And then in this plot, you can see on the left-hand side the perturbative results up to 4 loops, which within the radius of convergence agree very nicely with the black curve, which comes from the solution of an exact integral equation. And then on the right-hand side, you can see that it also agrees perfectly with strong coupling results coming from string theory. And this anomalous dimension and these calculations are really also very important for the development of integrability approaches, which is where this integral equation comes from. Now, this is limited to the planar case. And so I'd like to discuss in this talk what are the non-planar corrections to this. And to get a feeling for this, let's start by looking at the perturbative Wilson loops. Turns out that Wilson loops are really fantastic for understanding the color dependence. So this is particularly simple in the abelian case. So if we're just in QED but without matter, then Wilson loops exponentiate exactly. So the vacuum expectation value is just given by the one loop diagram, the exponentiation of that. In a non-abelian theory, so SUN theory, things are a bit more complicated, but one can still use that abelian exponentiation to have an effective description of what's going on. And the upshot of this is the following, that up to 3 loop order, these are the only color structures you can get. So you have an overall factor, which is the quadratic Casimir in the representation of the Wilson loop. And then we have quadratic Casimirs in the adjoint representations, the representation of the gluons. And this Wilson line analysis shows us that at each loop order, there's only one color structure. And the fact that there's CR out in front is called Casimir scaling. So this follows from properties of the Wilson loops. Now, it's interesting to look at the next order because there something new happens. So at 4 loops, there's one additional color structure, which involves quartic Casimirs. So these are trace of 4 generators in a given representation. And so then we have a term similar to what we saw before, and we have this new color structure. And here's some sample diagrams that would contribute to those color structures. I should also say that this color dependence is particularly simple in the Wilson line approach, but it's more complicated if you started, for example, from scattering amplitudes or form factors. So we can do the same analysis more generally, also allowing matter contributions. This will be very helpful to make a connection with QCD. And so it turns out then there's also quartic Casimir terms for the matter contributions. What's important for us is that they're linear. At this 4 loop order, they're linear in the number of fermions and the number of scalars. And because of that, we can write down a simple relationship, a supersymmetric decomposition between QCD and N equals 4 super Mills. Moreover, it turns out that these matter contributions, they're slightly simpler than the gluon one. They're already known, they've been known for a year. And therefore, computing the QCD answer or the N equals 4 answer is really equivalent. So naturally, especially in this community, we choose to do the N equals 4 calculation. But it will also give us, for free, the QCD answer. Now, there's another connection between N equals 4 and QCD, which is very well known, and that's the maximal transcendentality principle. So that principle says that the leading transcendental terms in this quantity, in the QCD result, give the N equals 4 result. And just to illustrate, let me show this for the QCD answer up to 3 loops, where I've set the matter contributions to 0. So this is the full answer, and you see the terms encircled in blue. These are the highest weight terms, the highest transcendental terms at each order, and those just give the N equals 4 answer. Now going to 4 loops, it's quite interesting that we can already have a test of this principle, because essentially it says that the highest weight terms come from the gluons. And therefore, the matter contributions should have less than maximal weight. And we can look at the known results for the fermionic and scalar contributions, and we see that they have at most weight 5. So that's lower than 6, which would have been the highest weight in this 4 loop calculation. So this also works here. Now, what else do we know? Well, in fact, there's a numerical result for the quantity we're looking for. So this came a couple of years ago through a very complicated form factor calculation. So these authors wrote down the form factor in N equals 4 super Mills and evaluated all these integrals numerically. Now, since they start with a pole of order 8, the numerical precision then goes down a little bit as you reach the second pole, which gives us the Cusp anomalous dimension. So I have this result, but it's got a rather large uncertainty. Now, in parallel, there's also been a QCD calculation using completely different methods. And they were also able to extract a numerical value for the QCD cusp anomalous dimension. Now we can use that supersymmetric decomposition I mentioned earlier and connect the two. And doing so, we see that the two numerical values are in complete agreement, but thanks to some more digits that we have in the QCD answer, we can translate that into more digits in n equals 4. And so this is the kind of a refined prediction. We'd like to know the analytic answer. I know that some of you might like to guess. So this is a place where you could try to guess what transcendental constants might correspond to this number here. And we'll see the answer later on in the talk. So just to recap this part of the talk, we've seen that the first non-planar corrections to the cusp anomalous dimension appear at 4 loops. The gluon terms at present are only known numerically. We like to compute them analytically. And thanks to the known matter contributions, it's actually equivalent to compute this in QCD or in n equals 4 supersignals. So let me say a few words about the method that we used. So this introduces a new quantity, which is, I think, very interesting in itself. It's the vacuum expectation value of a cusp Wilson loop. So it's a 4-sided Wilson loop with a Lagrangian insertion at a 5th point. So here the kinematics is such that the edges of a Wilson loop are light-like, but the Lagrangian is in a generic position. I'll tell you in a minute why it's interesting to consider this. But for now, let's just look at the lowest order. Computing this at lowest order, just evaluating those diagrams, you get this rational function. Furthermore, what's interesting is that this configuration is conformally invariant, which tells you that despite there's all these space-time points, it actually only depends on one conformal invariant variable. Moreover, it's kind of implicit in this formula, one can show that the definition yields a finite object. So what this is, it's an interesting finite function of one variable that we can study in n equals 4 supersignals. But how is it related to gamma cusp? Well, it's actually rather simple. You can think of this Lagrangian insertion as somehow giving you the integrand for the Wilson loop. And when we integrate over that insertion point, we get back the Wilson loop. And the Wilson loop in turn, it knows about the cusp anomalous dimension. So in formulas, when we take the derivative of a log of a Wilson loop, what we get is an integral over the Wilson loop with a Lagrangian insertion. And that's really the quantity we've just been looking at. So that's the quantity f basically from the previous slide. On the other hand, once we carry out the integration, on the left-hand side, we expect to see the cusp anomalous dimension in the leading divergent term. So in summary, what we see here is that we get the cusp anomalous dimension, but we're saving one loop order because we, for example, we just need to do this tree level calculation here. This rational function determines the one loop value of the cusp anomalous dimension. Or more generally, we just need the L-1 loop value of f to get the L loop value of the cusp. So how do we get f? We can use some tricks, which are based on the fact that f is finite and that it's conformal. So we can send the point x5 to infinity by using a conformal transformation. And you can see here that the function f is still a non-trivial function of one variable. So that's sufficient to determine f. But at the technical level, we gain a lot. And in fact, one can then see that the integrals that we need look very much like momentum space 4-particle scattering amplitude integrals. So for example, the one loop value of f is then given by this linear combination of box and triangle integrals. And well, the experts already know that this particular combination is actually finite, can be computed in 4 dimensions, and this is the value one gets. Now, let me illustrate how from there, we then recover the cusp anomalous dimension. This is a bit technical, so forgive me, bear with me for a minute. we saw that integration over x5 gives the cusp, but it's really an integral over space-time. One can show with a little bit of analysis that it can be represented as a functional that acts on a function of x. So here's this functional. Once we perform that functional that I'm going to define, we essentially get the cusp anomalous dimension. How is the functional defined? Well, basically you can say how it acts on a single power. So this power is replaced by this formula. For example, that means if you put a constant here, so you just put 1 here, that's p to 0, you get 1 back. So that's easy. But you can also get other things. For instance, if you want to represent a logarithm, you just expand this x to the p to the second term and you get its contribution. And more generally, we can apply this by writing f in a series expansion. So for example, with this one loop function we just had, both terms contribute and we find this value pi squared over 24. And if we keep track of the normalizations, then this is indeed the two-loop value of the cusp anomalous dimension. And this has been this connection has been established previously, and it's been tested up to the three-loop order. So in other words, the two-loop value of f reproduced correctly the three-loop value of the cusp anomalous dimension. So to extend this to the next order, we need to know what the integrand is for this quantity f. And just to see the structure, we expand here in the coupling. So we have the free loop computation here, a free loop contribution here. And now we have for the first time both a planar and a non-planar correction, which of course mirrors what we saw for the cusp anomalous dimension. Now, the Wilson loop integrand can actually be obtained from a limit of correlation functions. And this is a very powerful connection since there's a lot known about those correlation functions. And this means that the planar integrand is known to the order that we need. And also the non-planar integrand is actually known, was known up to a few coefficients until recently. And then I think toward the end of last year, the remaining coefficients were computed by a direct twistor space calculation. So in other words, the integrand is available. What's left to do is to perform the integrations. Now here there's a technical step, a technical point, which is really a subtlety, probably most interesting to the experts. So I'll just briefly mention it, but if people are interested, they're of course free to ask me later or also after the talk. The basic point is that, as I described, the function f is finite. It's finite in 4 dimensions, and it's actually better than a finite part of an amplitude, which might depend on the scheme that you use to define it in. This is just an honestly finite object, and therefore we should be able to compute this in 4 dimensions. Now, most of you will know that it's very tricky actually to perform space-time integrals directly in 4 dimensions. So we prefer to regulate and use well-established methods of dimensional regularization. But then it becomes a little bit subtle, because this finiteness actually comes about as a subtle interplay of the numerator and the denominator. And so therefore, when performing the calculations in d dimensions, we have to take care to preserve that finiteness. And so this is what we studied, and one can do it. It's not a particular problem, but it is rather subtle. That's why I wanted to mention it. So now, going further with the calculation, I already mentioned at the technical level, we get integrals that look like momentum space 4-point integrals. At the free loop order, there's also some new objects. Basically, you get new objects for 2 reasons. One is that you can have products of integrals, so they then cannot obviously be written in a planar way. And furthermore, we have these new color structures. And the upshot is that we get integrals that do look precisely like the integrals that we know very well, like a triple ladder integral. But we also get integrals like these, which we can be represented like these, which look a little bit non-planar, although they can be very conveniently described by dual coordinates. anyway, the upshot is that the integrals are similar to ones that are known, but somewhat different and also more complicated. So we had to have a separate calculation. This calculation, by now, it uses methods that are well established, uses the differential equation method. It uses a representation of the basis functions in terms of uniform weight objects. So that's very useful. And going through all these steps, we get the following canonical differential equations here. And I just want to highlight for the experts that the alphabet that you get is, the first part is the same as that you have usually in 4-particle scattering, but there's one additional letter. So this is rather unusual, I would say. What's interesting is that this letter is relevant for individual contributions to f. So individual integrals, certain individual integrals depend on it, but it actually cancels out in the sum. So as you'll see, the final result for f does not require this letter, but just is given by these 3 letters. So let me now come to showing you the results. First, this is a recap of the results up to 2 loops or 3 loops for gamma Cusp that had been known previously. So what I just said about the alphabet is translated here to the fact that one only needs harmonic polylogarithms to write the answer. Now going to 3 loops, we have the 2 contributions. Here's the planar result. So as advertised, is also just HPLs. They're all of uniform and maximal weight 6. That's what we typically see in N=4 results. And now going to the non-planar answer, the same is true. We have uniform and maximal weight 6. But we see one new feature. There's 2 terms, so which correspond to 2 different rational structures. And this is a little bit reminiscent of what one sees in non-planar 4-particle amplitudes. So now that we have these formulas, we can plug them into our functional and extract the full loop value of gamma Cusp. And here's the answer. So first of all, we reproduce correctly the planar value, which is given over here. So this is really an important verification that our method works, that the technical steps we've taken are all consistent. And then we get this new analytic non-planar value. So for those of you who guessed that's the answer, and it does agree with the previous numerical result that I showed you earlier. I should also say that after a paper where there was an independent calculation based on this form factor approach, where these form factor integrals were computed analytically, and that approach also agrees with our answer. Now, as I mentioned, this is equivalent to finding the Quartic-Casimir piece for the QCD anomalous dimension. So for this reason, and also because there had been a lot of work on all the other contributions, we were then in a position to present for the first time the full analytic formula for the QCD anomalous dimension at 4 loops. And here's the result in its full glory. So the first 5 lines or so are the non-quartic pieces, where now you have also a lot of pieces which depend on the matter contributions. And here encircled in blue is for the first time the quartic Casimir contribution for the gluons. And also here, just recently there was an independent calculation, again in the form factor approach, which verified this analytic result. So this already brings me to the discussion. So I've showed you 2 things. We considered an interesting quantity, which is the vacuum expectation value of a 4-sided Wilson loop with a Lagrangian insertion. And this is a finite quantity depending on 1 kinematic variable and on the coupling in N=4 Switbang-Mills. So I kind of argued that this is really an interesting quantity by itself. We computed that for the first time to 3 loops, including the non-planar corrections. And then we use that quantity to extract from it one loop order higher, the cusp anomalous dimension, which is given by this neat analytic formula here. And that then also allowed us to obtain the corresponding QCD result. Now let me close by making a few comments on future issues. The first issue has to do with that interesting quantity f of x. So because it's finite, to compute it in principle, all we need is its four-dimensional integrand. And I just wanted to point out that that thanks to work on the amplitude-hedron and recursion relations, we have a pretty good idea of what the planar integrand is. So, so here there's really a challenge to take that integrand and figure out what f is in principle at all loop orders, and that object, whatever it is, it knows about the cusp anomalous dimension, and it knows about the Byzard-Eden-Staudacher equation that I alluded to in the very beginning of the talk. So I think that's just a fascinating question to see if somehow where in this integrand we can really find the Byzard-Eden-Staudacher equation. Now, perhaps a more short-term application is the following. I mentioned the connection of the cusp anomalous dimension to twist-2 operators. So those anomalous dimensions are known for a couple of values of a spin, I think up to spin 8, depending on how you count. And now our calculation gives you the asymptotic limit for infinite spin. And of course, this is an open question. What is the analytic formula that represents all these results? Can one perhaps write some ansatz and bootstrap it? And finally, as I mentioned, one of the motivation was to provide some new information for integrability approaches. And I think it would really be fascinating if this non-planar cusp anomalous dimension can also be obtained from integrability. I'll stop there. Thank you very much.
Thank you, Johannes. Thank you. Now we have time for questions. I know Yara has a question.
Hi, Johannes.
Hi,
so I have a question. So in the formula for the form factor, you had this extra 1/1 plus x pole. You said there are two structures which are related to two different independent leading singularities in the 4-point non-planar amplitude. So this is an all loop order statement for the amplitude, that there are only two structures that can appear. Can you make similar statement here without doing any higher loop calculation? Just say there is nothing else which can appear than these two structures.
Right, yes. So I just to be clear, I said it's reminiscent of what we see in the 4-particle amplitude, and indeed this is very enticing. Here it comes about as an observation that there's these two leading singularities. We see that actually already before performing the integrations, when analyzing the integrand which came from those papers that I mentioned. And as far as I'm aware, well, you can probably make some statements about the planar answer, because that is tightly connected to the amplitudes. For the non-planar answer, this is not as direct, and we're really relying on either direct integration, direct calculations of the integrand, or on a limit from correlation functions. So, so perhaps one could say something along those lines, understanding better the integrands of correlation functions. Maybe a final thing to say is that there's also a very important interplay. I know I don't have it here now. That these, you know that for amplitudes, integrands have to satisfy many consistency requirements, in particular how they behave in soft collinear limits. And this can be in part used to obtain them. And a similar story is true for the correlation functions. So I think using such ideas, it may also be possible to obtain those integrands at higher loop orders.
Okay, thank you.
We have more questions. Yes, Omer, please.
Hi, so you seem to rely on a lot of cancellations between different contributions to get the nice form of the final result. And so maybe it's a stupid question, but can you ignore can you avoid some part of the calculation and assume that you're going to get the nice form and infer the result with half the work?
Yes, about this cancellation, well, I would like to kind of have an opposite view in a way, which is that for us, these cancellations in some sense a feature, because we have this general method that can compute those integrals, whether they're divergent or not. And they start with poles of 1 over epsilon to the 6 because they're genuine free loop integrals. And then we see that when we put everything together in the correct way, we actually do get a finite answer. And so this is also kind of an internal consistency check. So from that point of view, it's actually a convenient feature to have. But I understand your question. Of course, it would be nice to do something directly in 4 dimensions. And this, again, this can be in some sense seen already at the level of the integrand. So for example, some of the undetermined coefficients that were in the correlation function, once you put once you put the distances light-like such that you get the limit to the Wilson loop, you can see that only some of those contributions are finite, lead to a finite answer. So you can already get some additional constraints from that, basically by requiring at the integrand level that the object that you're going to calculate will be finite. So we do have a lot of control on that. Maybe just to finish on one final angle, I think for the perspective, it would be really great if one could calculate that directly in 4 dimensions. It should be possible in principle. For instance, there's been a very interesting work by Julio Parra Martinez and Enrico Hermann, which precisely is built on d-log integrands. And that's what we have here. We have in principle finite d-log integrands. So, well, it's probably a bit tough to go to free loops immediately, but I think given some time, this could be a way to go.
Yeah, thank you.
All right, David Kosover.
Johannes.
Hi, David.
Yes, thanks for the nice talk. I was curious about this extra letter. Is it connected to your introduction of gram determinants? Is it related somehow to an epsilon symbol?
No, it's not. I agree with you. It's really curious. It's actually, one can see it already in some very peculiar integral. So we have a kind of a toy version of it. And that integral was a potential term that could have contributed to final answer. It turned out that it came with 0 coefficient. So, it could have also, what I'm saying, this extra letter could have also appeared in the final answer. It's not, as far as I know, related to gram determinants. However, I will say the following. It did not come as a complete surprise to us. So I had come across it in a different context, which is when you consider 4-particle on-shell scattering, but now in 3, not in 4 dimensions. So basically, when going to 3 dimensions, you introduce a square root because the integrals scale in a different way. And that kind of suggests to you to make the replacement t going to z squared. And then in that new variable, you have the additional letter. In the new variable, you have a rational alphabet, and it does include the 4th letter. So that's another place where I know it appears. Yeah, for now, a curiosity.
Are there more questions? So again, I repeat, please raise your hand and I'll call you. All right. Are there any questions in the chat? No. All right. If there are no more questions, let's thank Johannes again.
Thank you.
So we can use reaction button right here.